Okay, this is problem number 2 in this set of problems that I put in a packet for you to take home. Before watching this video, I'd advise you to go back to Faraday number 1 and review the Bryan-Offit right-hand rule, which says point your thumb in the direction of the field you want, and your fingers will curl in the direction of the current you need. I'm again going to avoid writing down what's being asked for in this problem. Again, just to show you how the framework takes you pretty far before you even have to think about those things. So the first part's pretty easy. What is the magnetic field? Well, you're given the magnetic field in this case, and it is a constant, never changes.
So let's move right on to calculating what the flux is.
As we've seen previously, this is an example of a problem where the magnetic field is constant spatially, so it can be taken out of the integral. What's left over is just integral of dA, and that just becomes area. However, the area is not something that's obvious from the problem. We're given L as the height of the loop, but we're not told anything about its width, this dimension of the loop. So if that ever happens, just make up a number, make up a variable. Let's call it, in this case, we'll call it x. As usual, you should ask yourself which part of the flux is it that's changing that's causing an induced EMF. There's no change in angle. There's no change in magnetic field. That's a constant in this problem. So the only thing that could be changing is A. And if it's not L that's changing, then it must be X. And at the instant that this problem is beginning, we're told that the initial velocity is v. I added a little naught symbol to it because I think the original problem didn't have one, but I thought that was kind of confusing. So I'm just calling that. Because it so often happens that you're asked to find the current or to do something with the current, I went ahead and solved for that here. As you can see, the first part is already done. Whenever you've got forces and wires and magnetic fields, it's a pretty sure bet that you're going to be using some variant of this expression. Although it's not explicitly asked for, I think it's kind of a good idea to pause for a moment and think about the current direction, because that'll end up being useful thinking about the force direction. The nice thing, and one of the things I really love about this problem, is that we can think about the direction of the current and of the force in two different ways. One of them is with the Bryan-Offit right-hand rule, thinking about Lenz's law and so on. And the other is to think about what's going on inside this metal bar. You might recognize this as a rail current kind of problem or a rail driver. So let's go through these one by one. First, let's think in the usual way about how the flux is changing and how the loop would seek to oppose that flux. Here, you've got the bar moving to the right, which means as that bar continues to move, you see more and more and more field lines inside the area of this loop. That means that the loop is going to want to oppose this increase in flux. Now that we see that the loop is going to produce magnetic field lines that point out of the page to counteract the increasing magnetic field into the page, we can use one of two methods to think about what's going to be going on. One is to say, well, if you're going to have a current carrying wire that has a field that's out of the page to the left of it, then that wire has to carry current upwards. The Bryan-Offutt right-hand rule tells us that if we want to stick our thumb in the direction of the preferred magnetic field lines, then our fingers curl in the counterclockwise direction. What's also really interesting and useful to do in the case of this rail current is to imagine what happens to the positive charges inside this conducting metal bar. You could use the negative charges inside the bar, but you'd have to use the left-hand rule instead. After all, this bar is just made of ordinary matter, one presumes. So if you think about what happens to the positive charges that are moving to the right inside this field that points into the page, we see that there's a force on them to the upper part of the bar. Similarly, if you were to do the left-hand rule on electrons, electrons are moving to the right inside a magnetic field that points down, so you would get a force on the electrons that points down. So this is an alternative way to point out that there is indeed a current upward in that bar, which we had already figured out by other means here. Having finally established all that, we can go back and think about this cross product here and see fairly easily that if the current is carrying current upwards through L and the magnetic field points into the page, then the force on the bar is going to be to the left. There are so many reasons to love this problem. And the next one is that you're now being asked, seemingly out of left field, to develop an expression for the velocity as a function of time. Maybe you saw this coming because after all, the first thing you were asked to find before this was the force. And so relationship between force and velocity is something we've done a bunch of times. Notice it's at this point that I have to stop thinking about this as some constant v naught, because now we're trying to find what is the velocity as a function of time. This is an integral that we've done a bunch of times, and I don't really feel like trying to cram all this stuff onto this small piece of paper. If you need to practice with it, or if you have questions about it, please feel free to ask me. But I'm going to elide that whole part and simply point out that what you end up with in the end is an exponential expression. Now, because we have a velocity that changes over time, we have to replace this v naught here with the entire expression for v, and it gets a little bit messy looking, but it's pretty straightforward. Everybody unmute your microphones. I mean, come on. How cool is that? How cool is it that after reflecting upon it, we knew that had to be the answer anyway? Whatever the kinetic energy of the bar was, had to eventually be dissipated inside the circuit. So there it is, one of my favorite problems of all time, encompasses so many important ideas for Faraday's law, and ties in all sorts of cool stuff like conservation of energy and good old Newton's second law.